is the radial arm cross the linear momentum. In other words, r cross p gives me the angular momentum. So, let me derive the basic fact for you about that. So we have this angular momentum, right? What's the relation between angular momentum and torque? Now we know that for the linear case, we know that F is equal to dp dt, right? What's the analog of this in the rotational world? So what we should think about is, so consider, what if we differentiate the angular momentum? What's dl dt equal to? So this would be ddt of what? L is r cross p, right? Or we could write this as MRV if you like. I don't know, whatever floats your boat here. So this is what? This is dr dt cross p plus r cross dp dt by the product rule. One of many product rules, but a product rule nonetheless. And well, this folks, this is just m times v cross v if you think about it in terms of velocity, the first term. And the second term is assuming, well, that's r cross the net force. I should be clear, this is the net force, of course, but I'm really thinking about a point mass in this discussion, a particle. V cross v is what? You guys, this is low-hanging fruit. You should seize it. Did someone say 0? I just can't hear over the fan. This is 0. I mean, cross product of any vector with itself is 0. What's r cross f? Well, we just defined this a second ago. It's torque. So the instantaneous rate of change of the angular momentum is the torque. And so it's as stupidly simple as an analogy could possibly be. The torque, the rotational analog of force, is also equal to the time rate, instantaneous rate of change of the angular momentum with respect to time. And guess what? I derived it for a particle, but you know what? It's just the same for a system. If you look at a system of n particles and you study the net angular momentum as the sum of the angular momentums of the particles which make up the system, guess what? The net angular momentum is also the time rate of change of the net angular momentum of a system is once more connected to the net torque. In particular, if the net torque on a system is 0, angular momentum is conserved. So theorem, if the net torque is equal to 0 for system, that implies conservation of net angular momentum. So conservation of linear momentum and conservation of angular momentum for closed systems are two of the really the hallmarks, the quintessential results that must be known in classical mechanics. They're central to this field we're studying. They're really where it's at. In terms of results worth knowing and being able to explain, these are important. Momentum conservation is so very important. So I have an example or two I can show you. Let me show you. Listen, guys, we have one more day for rotational stuff. I have now showed you the main events. So past this point, we pretty much just have problems to work on. I guess I should tell you what's the unit for torque? No. It's a position times a force. You're not far off. It's a Newton meter. It's a joule. Now, I have heard certain professors say that it's wrong to say that a torque is a joule, because it's not a joule, it's a Newton meter. I don't know what that means. I think it's something philosophical because torque is R cross F, so it's a meter Newton. And if it's a meter Newton, then surely it's also a Newton meter. Okay, fine. And it's true mathematically that those are equal to joules, but
Is it just because the nomenclature is preserved for work?
I don't know.
Or is it not like an energy?
They know things I don't know. I don't know. It's a philosophical comment is my point. Ooh, these are nice examples. I'll do these next time. These take time to understand. I did want to show you guys this. This is the big picture. Here we have a rundown of all of my favorite analogies here. I personally found this very exciting when I was a student, and it finally dawned on me, oh, it's just like everything we already did. We just have to change the letters and think like there's analogies, strong analogies. If you could solve problems before, you can solve problems now too in kind of the same way. X has been replaced with theta, V by omega, A by alpha, M by I, F by torque, P, aha, this one we didn't get yet. Power is force dot velocity. Here now power is torque times, hey. Oh, torque times omega. There's an extra division by, I was about to agree with your watts comment, but I see now that this has an extra division by seconds. That's what joule divided by second gives me a watt. And this goes on. Kinetic energy translational, kinetic energy rotational. I just take the m and replace by I. These are the constant acceleration formulas. These are the constant angular acceleration formulas, right? And yeah, I don't know, it's pretty cool. You can, I should show you these examples next time. They take more time. Let me show you a simple one for the time we have remaining. Yep.
What lecture is that for?
27. Yeah, 27. All right. Here's a stupid example, but it serves our purpose. A compact disk is rotating with 3,000 revolutions per minute. What is its angular speed in radians per second? How fast is a point 4 centimeters from center moving? Exciting. So 3,000, this is basically just a unit conversion problem, but you need to be aware of these. So to convert from revolutions per minute to radians per second, I just multiply by 2 pi rads in a revolution, right? And then, I forgot rad was a saying, but I was watching this historical documentary on the CW or something this weekend about like skateboarding in the 70s, and like it reminded me that it was totally rad. I forgot about that, but brought it back for me. Sorry. Somewhat of a digression. Rad. And then a minute is the same as 60 seconds, so this is multiplying by 1 to suit our purposes, and we get 314 radians per second. The relation between the velocity and the angular velocity is multiplied by the radius. So here the radius is 0.04 meters, and so there you go, 12.6 meters per second. And then just for kicks, I converted this to miles per hour, and I got 28 miles per hour. What's the maximum revolutions per second on like a DVD? Do you guys know? Yeah, I think it's something like 10,000. So what would 10,000 be in terms of miles per hour? If this is 3,000, I think it's linear, right? So if you had 9,000, multiply that by 3, you'd get what? Yeah, about 90 miles per hour.
Like, you mean for a fixed point?
Well, that means that a point, if it's 4 centimeters in radius, I forget what it is, but it's actually like a physical limitation of objects. Like if you start spinning too fast, you can only have stuff stick together when it's rotating so fast. Oh, what? It just spun. There are in fact numerous YouTube videos of this. These slow motion photographer people. It gives them joy to watch things fall apart when they get to sufficiently high speed. Here's a slightly more interesting example. What's the kinetic energy of a rod of length L rotating with angular velocity omega about the axis pictured. So what I did was, and this is a really nice test question. It's right kind of in the right. This is like ballpark for a test question. So here you got to think about it as two pieces. You got this piece and that piece, right? Think of those as two separate objects, and they're both rotating. And so one has one moment of inertia, the other one has a different moment of inertia. They both have the same omega. So really I just have to figure out what's the moment of inertia for the right half versus the left half. So again, it goes back to 1/3 ml squared we derived last class, right? And so the 1L is L over 4, right? And over here. And that has a quarter of the mass. The other one has an L, quote unquote, of 3L over 4, and it has 3/4 of the mass. And so I add those together, that gives me the total inertia, 7/48 ml squared, and then the kinetic energy is 1/2 I omega squared, which is 7/96 ml squared omega squared. Everything else being equal, what's the maximum and what's the minimum moment of inertia you can have from the system by sliding the axis of rotation? Like, this axis can slide either over to this edge, right? Or over, let's say, over to this edge, but that's kind of silly. That's the same thing, right? So let's think about the midpoint, right? There are two sort of extrema. The one is where the axis is right in the middle of the rod. The other one is where the axis is at the end point of the rod. Which one of those two extremes gives you the maximum inertia? It's when it's at the end, right? That's what we derived. And so everything else being equal, it'll have more kinetic energy when you spin it around the end as opposed to around the middle. I think I talked about that last class. Let me shut up. One more example, then I'll shut up. Suppose you have a flywheel. And if you study popular mechanics over the decades, you'll find there's a flywheel. Cars are going to have flywheels, and cars are going to drive off flywheels. The future. This article is written about every 10 years or so. I haven't been reading popular mechanics for a while, so maybe it's finally fallen out of just.
I haven't seen one in a while.
In a while, okay. Here's why you don't want to do that. If you have 100 kilograms in a hollow cylinder, radius 25 centimeters, that's huge, okay? Outer radius, so it's a really big cylinder, and you go to 30,000 revolutions per minute. That's considerable. How far could you drive a car? How far could you drive a car using this energy if it takes 10 kilowatt hours to maintain 40 miles per hour? Assume you drive at a constant speed. So I work it out. And I'm assuming 100% efficiency. So all of my energy in the flywheel can be put into moving the car. And this flywheel will have about 55 megajoules. That's a lot, right? Seems like a lot. And so it's sort of a kinetic battery. It's storing energy in this rotational motion, right? And then, so just that's kind of more or less maybe what would be realistically possible in a flywheel you could put in a car. And that seems like something, but if you stop and think about gasoline, well, there about 130 megajoules in a gallon of gas. So you can have this giant spinning thing in your car that will get you about 1/2 gallons of gas worth energy. Oh, not to mention, do you want to be in a car when it crashes with a giant spinning metal wheel? I mean, you could also argue, do you want to be in a car when it crashes with all that high-octane gas? Yes, I've seen many crashes. The likelihood the gas actually blows up in the crash is only significant when it's a movie. Right?
Yeah.
Right. Gas is good. What gas means is that there are not horses in the street making messes everywhere that we have to walk through. Also, we can live relatively far from where we work. Also a good thing. I would add to the naturalist, where do you think oil came from? Why would you say oil's unnatural? It's part of the earth. It's just as natural as you and me. What's your deal? Get over with it. Sorry. All right, my spiel is done. Pro big oil, woohoo!
But you see,